Hello and welcome to Chapter 7, Strong Acids Mixed with Weak Acids, in which you will learn the process for solving those sorts of problems. You can use this exact same process for solving strong bases mixed with weak bases, those types of problems. So step 1, as always, identify the major species. Curious if it's species or species, or if it even matters. I'll ask a biology teacher sometime. So we have nitric acid and nitrous acid. There's two of them. So that means you list both. So nitric acid is strong or weak? I hope you said strong. Nitrous acid, strong or weak? I hope you said weak. All right, knowing that, I just want to make a quick note. One of these is going to go to equilibrium and one of them completely dissociates. Which one completely dissociates? Nitric acid. Which one goes to equilibrium? Nitrous. Okay, so knowing that, let's move on to step 2. Step 2, as always, is to write out the reaction or the reactions. In this case, we have more than one. We have HNO3, and since it completely dissociates, which type of arrow do we use? One-way arrow. And we have HNO2. What kind of arrow? It's weak, double-sided arrow. Step 3. Step 3 is to write out an equilibrium expression if there is one. So in this case, do we have something that goes to equilibrium? Your answer should be yes, we do. It is our weak acid, nitrous acid. So since it is an acid, what is my subscript on my K? Should be A for acid, is equal to the concentration of my products, H plus NO2 minus, over the concentration of my reactant, or reactant. Sure, there's probably water in there somewhere, but it doesn't factor in because it's a liquid. Now I need to plug in my Ka on here because it's given, so I might as well include it so I don't forget about it. 5.1 times 10 to the negative 4. Great. I'll set that aside for later. Now the next step usually is to do a dilution, but you have to make sure there's a dilution that's actually happening. So look up here. Do you have two different substances mixed together? Are the concentrations changed because of them being mixed together? Your answer should be yes. So do the dilution. Okay, so my equation for dilutions is always M1V1 equals M2V2. I need to do this for both of my substances, so I'll have one for HNO2 and for HNO3. HNO2 starts off with a concentration of 0.20 and a volume of 50 milliliters. We're finding a new concentration. Now let's figure out what its final volume is. It's mixed with 150 milliliters of 0.6 molarity HNO3. Mixed with. So do I add these volumes together, or is it just 150 milliliters at the end? The answer to that question is you add them together. It's mixed with it. You're mixing 50 with 150. So you have 200. So you end up with a M2 of 0.050 molarity HNO2. So now let's think to ourselves, is this the concentration at the beginning or the end or both? This is initial concentration. Do we know the final / equilibrium concentration? Not yet, we don't. Okay. So that's done. Now let's do the same thing for our nitric acid. Starting concentration of 0.600 molarity, starting volume of 150 milliliters, new concentration, new volume. So new concentration for this one, I have, I think, 3 sig figs, so it'll be 0.450 molarity nitric acid. Now, is this initial or final? It is initial. And do we know the final for this one? Your answer should be yes, we do know the final. We know it's a strong acid. It completely dissociates, which means it falls apart completely. So you could say it's 0 molarity at the end. So cool, we figured out the concentrations for that. Woo! Drawing boxes is fun. Okay, now, as far as figuring out the concentrations of the hydrogen ions, for our nitrous acid, the first one, or sorry, wait, yes, nitrous. For our nitrous acid, can we figure out the concentration of our hydrogen ions yet? The answer is no, because we don't know how much nitrous acid there is at the end, so we don't know how many hydrogens are released. Same thing with our nitrates, we just don't know. However, we do know that our nitric acid is completely used up, which means we should be able to figure out the concentration of our hydrogen and our nitrate ions. We have a 1-to-1 ratio between hydrogens and nitric acids and nitrates and nitric acids, so these concentrations are just going to be exactly the same. And for those of you who have trouble figuring this out, you could always do it the long way, where you say, okay, I know I have 450 molarity HNO3. For every 1 mole of HNO3, I have 1 hydrogen. So you can see it's a 1-to-1 ratio, and that gives you the same number. You can use that to figure these things out if you want. That's just a little side note. Okay, so I've got that. Can I box this hydrogen concentration? The answer to that is no, because I still have some hydrogens that are going to come from this nitrous acid, so that won't work. However, will my nitrous acid contribute to my nitrate concentration? No. Nitrate is only coming out of nitric acid. So that's boxed. All right, next step. What do we do now? We're going to try to figure out equilibrium concentrations from our nitrous acid. So what do I have to do in order to figure that out? We have to make an ice chart. Yay, ice chart. Set up ice chart. So let's see, I need the equation across the top, HNO2, double-sided arrow, H and NO2 minus ICE. Okay, so this is going to be a little bit different than usual. We have a new contributing factor. So we know our initial concentration of nitrous acid. We just solved for that in our dilution step. Our concentration of hydrogens, usually we'd say, well, the nitrous acid hasn't fallen apart yet, so I don't have any of these ions. But that just isn't the case this time. Sure, I don't have any nitrate, but if you look down, I'm going to put a green star next to it, right here, we have some hydrogen ions that are going to contribute to this ice chart from the nitric acid falling apart. We're assuming that these hydrogens are present at the beginning. So you throw them in there. There they are. They came from your HNO3 dilution. Okay, well, I still don't know any equilibrium concentrations, so assume something is equal to x. Something without a coefficient usually makes your life easier. So this becomes 0.050 minus x, 0.450 plus x, and just x. All right, well, let's move on. Let's try to actually solve for some of those x's by plugging into our equilibrium expression. So we've got that from over there. So I know that 5.1 times 10 to the negative 4 is equal to, okay, concentration of hydrogen, that's 0.450 plus x times x over 0.050 minus x, products over reactants. I don't have any exponents because nothing has a coefficient. Okay, so I'm sure that you, as well as I, do not feel like solving a quadratic equation, so instead we are going to assume x is small. We could say small x assumption. And if that's the case, then that means that this x goes away, and oh, so does this one. Hey, that's nice. So now I can solve for my x very easily. So let's do that. X is equal to 5.7 times 10 to the negative 4. Let me just double check something. It'll be 5.1 times 10 to the negative 4, 050 divided by 0.450. Okay, so yeah, 5.7 times 10 to the negative 5. Okay, cool. So before I can do anything with this x, I have to prove that this is valid using the 5% rule. So you don't have to create an actual step for this. You could just say check 5% rule. So you need to show that 5.7 times 10 to the negative 5x divided by what you're comparing it to. So I'm going to pick the one that is more difficult to pass this test. So which one is more difficult to pass? Let's see, 5.7 times 10 to the negative 5. So the one that's more difficult to pass this test is going to be I don't know why my brain's not functioning right now. I'll just do both of them. Why not? So let's do 0.450 times 100 equals, and to save space I'm going to double up. I'll put the other one here, but you should not do that on yours. You need to make it nice and neat. Oops, times 100 equals. Okay, so let's see. The one that's divided by 0.05 is going to end up being 1.14 times 10 to the negative third. Well, I know that's less than or equal to 5%, so that one's good. And now my other one is 5.7 times 10 to the negative 5 divided by 0.45. That'll give me, times 100. This is 0.013, which is definitely less than 5%, so that one's good. I think I forgot to multiply the other one by 100, so let's fix that. So this ends up being times 10 to the negative 1. Oh boy. Times 10 to the negative 1, still less than 5%, so we're still good. Cool. All right, so now that I have that, I can actually use my x to figure out different concentrations. So I know that the concentration of my nitrite is just equal to x. So that'll be 5.7 times 10 to the negative 5. I can box that molarity. How many sig figs did I have there? Just 2 from that 0.050. And 2 from my 5.1. Okay, that one's done. I can figure out my HNO2 concentration. I know that. So I'll do 0.050 minus x. So let's do that. You'll end up with 0.050 minus x. I'm going to put two equal signs on the same line. I told you guys not to do that, but I'm trying to save space. So there. Ha. This one ends up also being 0.050 because x is so tiny. So that's my HNO2 concentration. Now I can figure out the concentration of hydrogen ions, and that'll be equal to 0.450 plus x, which will give me, oh, look at that, it stays the same, 0.45, whoops, 0.45 molarity. Pretty cool. That is done. So this problem, however, also wants the concentration of hydroxide, the pH, the pOH, and if it's acidic, basic, or neutral. So I need to scroll down to make space for that. There. Okay, I'm going to move over to the other side. So let's just do this. So I'm going back over here. So now I'm on to step 7, which is to solve for pH and pOH, and in this case, the concentration of hydroxides. So we know that pH is equal to the negative log of the concentration of hydrogen ions, which is equal to the negative log of 0.45 molarity. So my pH, let's see, I want 2 sig figs, so that means it's going to be 13.65. Remember, it's only the decimal points that count for the sig figs when something goes through a log. So there's that one. And now for my pOH, well, I know that pH plus pOH is equal to 14. By the way, this part of the process you should be able to do without me. pOH is equal to 14 minus the pH, which will give me, ooh, I did the math wrong up there. Dang it, I'm sorry. Let's go back. This is what I get for rushing. I always make lots of mistakes at the very end of a video. Smooth sailing until the very end. Okay, let me make this eraser smaller. All right, that goes away. Oh gosh, it's red. Eraser. I can just imagine you tapping your feet, waiting, going, come on. There. Okay, let's try that again. The pH is equal to 0.35. If you plug that in your calculator, that's what you should get, which would make my pOH equal to 13.65. Awesome. So I can tell if it's acidic or basic based off of that, or neutral. What do you think? Very, very low pH means it is acidic. Now finally we need to find our concentration of hydroxide ions. So I know that here I'll do this on the side, the POH is equal to the negative log of the concentration of hydroxide ions. So I'm going to move this negative symbol over to the other side, and now I'm going to I need to get rid of my log, so I'm going to use the base of log, which is 10, base 10. That will help me get rid of this. That goes away. So now I end up with 10 to the negative POH is equal to the constant. Oops, I didn't mean to use green. Oh well. And I'll just keep using it, I guess. That means I have 10 to the negative 13.65 is equal to the concentration of my hydroxides. So I guess I'll switch to red now. My answer is 2.2 times 10 to the negative 14th. And remember, it's a concentration, so don't drop those units yet. Keep them. Whew. All right, so that's that problem. I'd recommend going over this one again now that you've watched the video, because there were a lot of new things that we did. Okay, I hope that helped.